Welcome back to the Machine Learning for Engineers course. We're going to be doing a second case study on the same data set that we used before. Previously, we used the concrete strength data that came to help us do visualization of the data and be able to recognize outliers and other things. Now we're going to take it one step further. We're going to do visualization, but also classification and regression. So if we look at this, the business objective is that we want to be able to classify concrete into high strength or low strength and be able to predict what the strength is going to be. So we do have some data. We're going to consolidate. We're going to do some more visualization just to review it. And then come down here to outlier detection and filters. We'll scale the data. And then we'll split it into these train, validate, and test sets. In this case, we won't be doing hyperparameter optimization, so we'll skip the validation set. And then we're going to be looking at the label, in this case, high strength or low strength, or also the CS-MPa, the concrete strength in megapascals. And then we'll do some classification and then also regression. So we're going to step through this, but let's go to the course website. The link is also right here. And if you come to this homepage, then come down on the right to applications. And here is the concrete strength case study. So we're going to come down here to this data set. We have the cement of the mixture, concentration of the cement, slag, fly ash, water, superplaster, coarse aggregate, fine aggregate. So all of those are concentrations, kilograms per meter cubed. And then the final one that we have as a feature is the age. And then we look at the concrete compressive strength. So that's the thing that we want to be able to analyze. And we have these 1,030 concrete samples. So this first video takes you through some of the visualization with Seaborn, with Pandas, with Matplotlib, and Plotly. And so if you want to review that, go over this one first. The second one is this one right here on Jupyter Notebook on GitHub, or you can open it up with Google Colab. I'm going to go ahead and just download a copy of this. Okay, and here is the notebook, and you could either clone the archive or you could do something like copy the source. It's just a JSON file, and then open up a new text file here, and I'll just call this concrete.ipymb. Okay, I'm going to paste that in here, and this is going to be in Notepad. Okay, I'll close it, and then now I'm just going to open up that on my desktop, concrete.ipymb. So there's the notebook. You saw the source code for it, and you can do it in a variety of ways. You can download the whole archive and extract it, or you can just get that one in particular. All right, so this is the case study. We're going to be looking at this data set right here, just like we did previously. And it's 1,030 samples of these comma-separated values, or CSV file. So there it is in text format. You can also open it up with Excel if you like. Okay, let's come down here. Here are some packages that you're going to need to run these modules, to run these problem statements. So I've just included all of the imports here that we're going to need today. And often you could just take it as a template, go ahead and just import it and copy it into any future code that you use. Many of these sklearn classifier models, or we also have regression models here as well. Okay, so here's the data, and we're going to just read this and maybe even view the data. So I'll just do head and go ahead and just look at the first part of the data. Now we want to create a pair plot with the data. So this one is going to be Seaborn, and I import it as SNS, and this is pair plot of this data. Okay, so after it finishes running, we're going to see this pair plot of, it's going to take a little while to generate all of it, where we see along the diagonal elements. I'm going to go ahead and close this just so we can make this just a bit bigger. Here we can see along the diagonal elements, we have the distribution of that variable. And then on the off diagonal, we see this variable related to CSMPA. So there's cement. You can see a positive correlation between those two. Slag, that one, it's not necessarily determined, maybe even a little bit of a negative slope. You can see fly ash has many zeros in there. There's water, superplasticizer, coarse, and fine aggregate, and then the age as well. And then you can see the distribution of concrete strengths. The median value is 35. Okay, so right here. All right, let's go ahead and divide between the high and the low strength. So in pandas, we can do that where we say we'll create a new data and then call this one strength. All right, and then we're going to set it equal to something. And we want to set it equal to high or low. So instead, before doing this, before assigning it, let's go ahead and just look at what we can do with NumPy where. All right, so NumPy where CSMPA, that's the strength, is greater than or equal to 44. We'd call that maybe high strength concrete, and then the other ones are low. Okay, so if I print this out, I would then get an array, a NumPy array of highs or lows depending on what the values are. So we had high, high, low, and if we come up here to our data, we say high, high, and then that one's below 44, so it would be low. All right, so let's go ahead and make a new column. And we do that by just saying data strength equals that. And then let's just print out data head again. All right, so we just added a new column here where the strength is either high or low, depending on if we're greater than or equal to 44 or not. All right, so this is just the data preparation. Let's go on to data visualization and cleansing. So this is a little bit of a review about what we just already did on the prior video. But let's go ahead and just do that again with some of the summary statistics. Okay, we can describe this. You can see that we have 1,030 samples of each of these. There's the mean, and so you can see the mean is 35.8. Okay, the median value is 34.4, and there you can see the quartiles, for example, and the standard deviation of those. All right, let's check for balanced data between the high and the low. And we want to have about equal categories between them. The other thing we can do is, in addition, before we go on, this is describe, but if we want to do something just a little bit more informative, we can also run this profile report with, and this gives us a much more detailed exploration of the data. Okay, so it's pandas profiling, and it generates these, with the 1030, we can come over here to variables, and then we can see some statistics on each of those to get a little bit more insight into the values. I see that I have high is 294 and low is 736. So that's what we're looking for in terms of the balanced classification data set between high and low. So if you have imbalanced data, one of the things you may want to consider, this isn't terribly imbalanced here, but if we need to do a better job of balancing the data, there's another section here in the course about how to deal with imbalanced data and learning with that. We can undersample the majority class or oversample the minority class, but I'll leave that up to you if you want to go down that route. But for now, we'll just look at and see that, hey, we have 294 high and 736 low. All right, but let's, if we didn't do pandas profiling, we can also do something simple with pandas. All right, so this is the strength, and we'll do value counts. Okay, let's see, value counts, it did not like that. Value, oh, I need to do value underscore counts here. All right, so here's a value count between low and high as well. That's a simple one-line way to do it. And let's also just generate, this bar chart of, just go ahead and do this to just visually represent this. I can do plt.bar, and this is going to be x equals, and then I'll have low and high as the two axis values. And then the height is going to be equal to data strength, and then this will be dot value counts. Okay, so you can see it graphically as well. I mean, the numbers are nice, but sometimes it's good to see the balance of data, especially if you have multiple classes of data that you want to be able to see on the same bar chart. All right, so let's just convert, in some ways these strings are good. They're more readable for us, but maybe we want to maybe have the computer be able to analyze some things. We need to convert that into numbers. And so we can use one-hot encoding to translate text to a number, like binary numbers. But let's just first of all look at the data types of each of the columns. So you can see most of them are float 64, so 64-bit floating point numbers. But we do have the age that's an integer, and then the strength that's an object. So those are strings. Okay, and let's go ahead and convert those. All right, so I'll insert another cell below. This one, I want to say data.strength. Okay, I can either do the square brackets or I can do the dot to reference that. And I'll say 1 if x is high, else 0 for x in data.strength. All right, and let's just print out the data head. So you can see I've just converted them to ones and zeros using this one line if statement, and then I just cycled through all of the data strings. So took all of them, converted them to ones and zeros. So let's do some data cleansing now. Let's come down here. There's one row or multiple that contain outliers. Identify the outlier with box plots. So let's do data.plot, and the kind in this case is going to be equal to box. And you can see all of the data on a single plot here, but sometimes this doesn't make sense because you have some of them that, plasticizer concentration, for example, maybe that's a very small value. You don't want to necessarily have it mixed in with cement concentration or fine or coarse aggregate as well, which have much higher values. So one of the things that we can do is just do subplots equals true. Okay, and that will put it all on the same plot. But again, this is doesn't look very good. Okay, so maybe we want to spread it out over a little bit, maybe 2 rows and 5 columns. Okay, and that's better. But let's also just say the figure size. We're just going to say that it's equal to 12 by 8. Okay, so make it a little bit bigger just so we can see each one, spread it out, especially when you have a lot of, data columns, everything's going to look a little bit squished. So I've just put that into 2 rows and 5 columns. And you can see some evidence here of maybe some outliers, some, very long age. Maybe we want to do something like put the natural log of the age here. So you can do nonlinear transforms so that as it gets older, it doesn't influence it as much. Also, it looks like the fine aggregate might have an outlier there as well. All right, so let's go and just view the outliers. Let's look at those particular rows. So I'm going to say, possible outliers equals, and then let's look at data, and we'll do location. We'll do the location where this is equal to, is going to be true. Okay, so let's go ahead and just say data fine aggregate, and that one is greater than 950. Okay, and then I can say, let's look at outliers. Okay, so there's greater than 950, but let's say I also want to include some where the slag is greater than 350. Okay, so maybe just look at those points right there. And so then I can say or, and then just copy this. Let's see, there it is, and then this is going to be the slag is greater than 350. So this is an OR operator, a bitwise operator. If you want to use AND, then you just use the ampersand. Okay, so this is OR. So if either of those are met, then I'm going to include it in this data set. And I think I may need to separate this, so I'll put parentheses around it so it does these operations first and then does the OR. All right, so here I have it. I have all of them where the fine aggregate is greater than 950, and then I also have let's see, where's the slag? Okay, so I have the slag if that's greater than 350. So I have a couple right here where the slag is potentially an outlier. So let's just remove those. I don't necessarily know if those are outliers or not, but let's just practice removing some of those values. So I'm just going to copy this, and I'm just going to say that my data equals anything where both of these, so if this is true, and let's see, I'll do this. I'll rearrange it so if it's less than 950 and less than 350, then I want to include it. So I want both of those to be true. If one of them is false, then this is all going to be false and it won't include that. All right, so let's just do length of data. All right, so I've reduced it. I went from 1030 down to 1023. And so I've reduced by 7 the number of data sets that I have, data rows that I have. All right, so let's just verify that the outliers are removed with another box plot. And so let's just come up here and copy this. I could run it again, but just to do it sequentially, I'll just create another one down below. All right, so it got rid of the slag outliers and then the fine aggregate outlier there at the top. All right, let's go down to data correlation now. So we want to generate a heat map of the data correlation. And what I can do here is SNS heat map and data.corr. Okay, so let's just look at that first. Okay, data.correlation, and there I can see just numerically this matrix, but I want to plot it now. I want to create a heat map so I can look at that visually instead of okay, so here it is, and you can see maybe I want to change some things about this as well. Let's change the color map, and I can change it to cm.spectral R. So there are a couple different options for that. You can many different color maps that you can use depending on what you'd prefer. All right, and then if I want to make this just a little bit bigger, let's see, I'm going to try fig size here. I don't think it's going to work. Okay, so that didn't work. So what we have to do instead is we're just going to say the axis. Okay, so we're getting an axis handle here. And I'll say create a figure with figure size equals, and fig size equals 12 by 8. All right, and then I'll get the current axis handle, get current axis, okay? And then put that in right here. So I've already generated the figure. I've said it's that large, and now you can see it's much bigger, maybe a little bit easier to see in this, if you have, especially if you have a lot of variables. Okay, so we've taken these values right here, this matrix of correlation values. If it's equal to 1, it's perfectly correlated. -1, it's perfectly negatively correlated. And then 0 means no correlation at all. So kind of this yellow right here in the middle, very little correlation on these points. Okay, so let's go on to the next one, which is data distributions and pair plot. So I'm going to just create data pair plot, and I'll just create a copy of my data. All right, and then I'll say the data pair plot. I'm going to convert my strength back to some strings instead, and this is going to be numpy where dpair strength equals 1. Then I'm going to say that's high and low. And I want to do that because it's going to look a little bit better when I create this pair plot. And then SNS pair plot, dpair, and hue is going to be equal to the strength. Okay, so this one is going to generate the same pair plot, but instead of just all of the data, it's going to show it separately by high and low values. Okay, and when it comes up, then we'll see now we have the low strength and the high strength. So the low is going to be this in orange, and the high is in blue. And you can see that right here, the CSMPA, the two distributions of those. And we can see it's just perfectly divided here. But let's just look at some of these other ones that we have, especially these distribution plots. The cement concentration, you can see the low strength typically has less cement. All right, and then slag also typically 0 slag for, but you know, it's kind of hard to tell if that's a contributing factor. Okay, fly ash, we have water. Okay, maybe some more superplasticizer relatively for the high. And then coarse aggregate and fine aggregate looks about even on the distributions. And then we have age. So age, it looks like maybe just a little bit older for the high strength. All right, and then we can look at some of the pair plots here between the two and see if there's a correlation, just looking at the relationship between the two variables. All right, so that's it with visualization. It was somewhat of a repeat of what we covered last time. And now we want to go on to classification, which is part 2 of this. We want to train and test a classifier to distinguish between the high and the low strength concrete. So this high and low, and test at least 8 classifiers of your choice, and we'll recommend a best classifier among the 8 that are tested. So first of all, we want to divide the input features X and output label Y. So that just says these are all of our inputs, and then this is our outcome or output. All right, so what we want to do is just, I'm going to say Y name. All right, and that is going to be equal to the strength. And then my X names, okay, that's going to be a list of all the data columns, but I'm going to remove one of those, okay, the strength. I'll remove strength, or I could just put Y name in here. Okay, and let's also remove the CSMPA. Okay, and that's the numerical value that we then converted into strength, high or low. All right, and then we can print X names. All right, so here are all the X names that we had. We just took all of the data columns, removed the two that are our outcomes or outputs or labels, and now we want to do some scaling on this data. All right, so I'm going to just also copy these. I'll insert another cell below, and I'll just say my X data is going to be data, and these are going to be the X names. And I'll just copy it so it doesn't create a slice. I can just make a separate instance of this. Now you may not want to do this if you have a very large data set, because it's going to just create copies of data that are repeats of each other. Okay, but in this case, it's Y name. It's not very large in terms of the data. Okay, data scaling now. We're going to use a standard scaler, and let's see, scalar. Okay, and then we'll have our X scaled data. And to get this, we'll use a fit transform. And we'll fit and transform this X. So what it does is it comes up with the scaling factors and then scales it for us and then returns it as another data frame. Actually, it returns it back as a NumPy array. Okay, and we can see that it's going to be a NumPy ND array. So we need to convert that back into a data frame. And I'll just say that my columns equals X dot columns. Okay, let's just look at this. Okay, so I just have all of my input features that are part of that. Okay, so this output label is not going to be scaled because it needs to be a categorical data as an integer instead of a continuous real number. So if we scaled the Y value, it's a 1 or 0, the output, then it's going to be, we need an integer value. We need a 0 or 1, a high or low, some kind of integer value instead of a continuous value. Okay, so let's go to the train test split. Now in this case, we're going to have X train and X test, Y train and Y test. And I'm going to use the train test split, and this is a function that is available in scikit-learn or sklearn. And I'm going to have this XS, there's my Y data, and I'll say that my test size is 0.2. So I'll save 20% of it for testing. All right, I'll shuffle it. So it'll randomly select from that, and then I'll just give it a random state. This helps you reproduce it, reproduce the results, but still have it randomized with this seed. And I'll just say that's equal to 42. Okay, and then maybe I want to just print out the length of X train and X test, just to make sure I got about the right split between the two. So you can see about 20% of them are saved for the testing. All right, now what we want to do is just evaluate the best features. And I'm going to use select kbest, and we've already imported it. Select kbest, and this is going to be a classification. So I want to use the metric for that, and k equals all. Okay, and then we'll fit skbest fit, just like we do with our other classifiers, X train and Y train. All right, and then we're going to get the fit scores. So this one, I'll just go and print these out. First of all, fit scores. Okay, so you can see the fit for each of those, but let's plot those so it makes it look just a little bit better. All right, I'll have scores. I'm going to convert this back to a data frame and put a dictionary in here that my features are going to be the X-train columns. And then my score is going to be the fit dot scores. Okay, I'll just create that dictionary. Let's see, features. I made a mistake here. I added this extra one. Okay, so there's my dictionary. I have my scores. And then let's go ahead and just set the index of this to the features. I'll set the index to features, and I will drop equals true. So I'll drop the current index. I don't need to hold on to that. It's just going to be numbers anyway. And then I will plot it. Kind equals bar. Okay, and then let's just go ahead and do that. Okay, so here are the scores from Select K Best. So it looked at the significance of each of these input features. And as we saw before, slag and fly ash, we even had coarse and fine aggregate. Those didn't have a lot of effect that we could see visually. The ones that have the most effect, it said cement is the most. And then we have water, superplasticizer, and then age. So those are going to be the most impactful for this classification. Okay, let's go to also I'll insert cell below. Let's just see scores as well. Okay, this is the table that we came up with, the data frame. When you can see features is the index, and then we have the score. And it just helped us be able to create that nice plot. Okay, so let's go ahead and just do train and test with a logistic regression. So I'll create my new logistic regression model. All right, and then I'll do LR fit with X train and Y train. Okay, and so I can fit it, all right, but then what I want to do is just look at the confusion matrix. The confusion matrix will tell me how many misclassifications I have. All right, here's my model that I trained, and then I have X test and Y test. All right, so here's the predicted label is 0, true label is 0. So this said I predicted that it was going to be a low strength concrete, and it actually was a low strength concrete. And then this is when I predicted that it was going to be a high strength concrete, and it was also a high strength concrete. But you can see that I predicted some high strength, some low strength when it was actually high, or some high strength when it was actually low. So these are the misclassifications here. You can see it's 37 of them are misclassified, whereas 168 are correctly classified. But one of the things that might be problematic about this is if it predicts that it's going to be a high strength concrete, but it's actually low. So this is maybe the most severe type of faults detection, is that it says it's going to be high, but it's actually low. So for applications where you need high strength concrete, that's going to give a false answer. Okay, let's go ahead and train 8 classifiers. So that was just one, just to show what we're doing. But let's just come up with 8 of them. I'm just going to copy these in. So here's 8 that I chose, and I'm just going to give those some names. Okay, so Here are the names of those. And I'm just creating a list just to be able to see those just a little bit more easily. All right, and then for each one of these, for classifier, name in classifiers, I'm going to take each one, CLF, that's going to take NB, DT, K, and N sequentially and fit those. And I'll use X-train and Y-train. Okay, so it's going to fit all 8 of those, and so it's done. Now we want to evaluate the classifiers, and we'll report the confusion matrix for each one. So I'm just going to start with I equals 0 here because I need a counter, and then I'll create a new figure. I need to make this plenty large because I've got a lot of confusion matrices to display on a single plot. All right, and I'll do this again. I'll just cycle through all of them. And I'll increment this I value just for the plot. Okay, and that will be subplot 2, 4, I. So I have 8 of them. I'm going to have 2 rows, 4 columns. And then let's go ahead and just plot the confusion matrix. Plot confusion matrix, and I'll have my classifier, my X test, and my Y test. So we need to use the ones that we didn't train on, and then I'll say that there's my axis, so that's where I'm going to plot it, and I'll include a title for each of these. It's going to be the name of the classifier. All right, so I need to do that as a semicolon. Or I can just create a new line like this. Okay, so it looks like this is a deprecated warning. All right, I might have to go and get a different one. But you can see it still worked in this one. And you can see the rate of false positives, false negatives. So false positive means that in this upper right-hand corner, we said it's a 1, but it's actually a 0. So we predicted 1, it's actually 0. This is our false positives, false negatives. All right, so we have all of these. You can see the performance. The neural network did well. The random forest classifier also did really well in terms of especially this one right here in the upper right, where you predict that it's high, but it's actually a low strength. And then the other ones were about the same. Maybe decision tree was up there, but naive Bayes, k-nearest neighbor, support vector machine, logistic regression, those, and also stochastic gradient descent, those all didn't do so well. Random forest classifier, neural network did the best on these, and decision tree was just right behind it. Okay, so let's go on to regression now. So now we did classification. Regression is where we're going to try to predict the tension strength or the compressive strength. And we want to compare the predicted concrete strength with the regression model. So let's just scale. We're going to just start with our data. We'll create a new standard scalar. In this case, I need to scale the concrete strength, the output, in addition to the input features. So as opposed before with classification, you don't want to scale the 1 or 0. So I'll have my scale data and I'll fit transform, and I'll do that on data. Okay, here's my scale data. I'll convert it back to a data frame. Okay, and then what I want is the head of that just to be able to look at it. So now I've scaled all of these values. This is the scale data before it was a range, some large, some small. But if I describe this as well, I'll see some of the statistics of it. Standard deviation is going to be 1. and the mean value is 0. So it scales everything to a mean value of 0, standard deviation of 1 with this standard scaler. Okay, let's go on and just select our features. We have these 8 concrete properties as input features, and the output label is CSMPA. Let's divide these into sets that contain the input features and output label, and then save it. Okay, so let's go ahead and say that y name equals, and this one's going to be different this time. It's CSMPA instead of strength. And then the x names, we'll create that list again, and that'll be our data columns. And I'll just take the first 8. So I can either have all of them and remove the last 2, or I can just say, give me the first 8. All right, let's have our scaled values are going to be x names, and these are going to be the values of those. And then the y scaled are going to be the data frame. I'll just do y names. So I'm just going to get a NumPy array here instead of the data frame. Let's see, where y names. Okay, I did that again. Okay, so there's my data, and then we also want to just take a look at select k best. Let's go back up and just grab that for select k best, and then we'll just change it to the regression evaluation instead of for classification. Okay, so instead of F classification, we're going to do regression. And I think that's all we need to do. And so it gives us, maybe slightly different scores here based on if it's regression or classification. It looks very similar to the last one. Let's see if that's about the same. 140, a couple and 100, then age is around 40. Okay, it looks about the same to me. Okay, so maybe because we've scaled the data, and so it comes out as similar. Okay, we want to split the data, and let's use something similar to last time as well. We're just going to take our XS and YS values instead, and go ahead and create this split. Okay, if you want to continue the line, if it gets too long, you can put that continuation character there and maybe add others if you'd like to kind of keep it on the same screen if it starts scrolling over. All right, and then we have regression fit. So let's just come up with these 4 that we have. Okay, I'm going to use just these 4: linear regression, support vector regressor, k nearest neighbors. I'll say that nearest neighbors is 2. And then I also have the neural network regressor, so MLP regressor. And I'll have some hidden layers, 3, 5, and then 3. I'll use hyperbolic tangent. I'll say there's early stopping and put max iterations equals 10,000. So if you get a warning that it didn't converge, you can always increase your max iterations if you need to. All right, and then I'm going to give these names as we did before with the classifiers. Okay, so the linear regression, support vector regressor, k nearest neighbors, and then neural network. And then I'll say for method and name in regress. Okay, so it's going to go through this list of each one and assign each one method and name. And then I'll take the method and I'll fit X train and Y train. Okay, so it's working on fitting each of those. It's come up with a fit, and they're all stored in these either LIN, SV, KNN, and then we could evaluate those. So let's do a validation now and look at the R squared for these. Okay, so let's see. So for method name in regress or for regression, the R squared is going to be method score, and we'll use X train and Y train. So let's just look at, for each one, we'll look at the R squared just on the training. All right, and then let's insert a cell below, and then also look at it on the test sets. Okay, now you should expect these to be higher because that's the data that you used to fit. This is the test data that it hasn't seen yet. So the one that did the best is this fourth one, which is a neural network, followed by, let's see, this is interesting. The K nearest neighbors was really high for the training, but you can see it dropped down to 0.64. So very highly correlated, this correlation coefficient. If you approach 1, it's better. 0 is not as good. This isn't a perfect metric, but it can be used as just a quick metric to say, how well did I do? You can see this one, the support vector regressor, this third one did really well on the test set, and about the same on the training. Okay, and linear regression looks like it did the worst for both training and testing. So let's go on to a parity plot now that just looks at the predicted versus the measured values. So this is a good way to see the overall fit of the tension or compressive strength of the concrete. And in this case, I'll go ahead and create a new figure. And let's make it just a little bit bigger. Here I'll do 10 by 10 on this one. And I'll create some subplots here. Okay, for each one, I'm going to create a plot of how well they did. So for method and name in regress, then I'll increment this by 1. And let me create a new subplot. And I'll do a 2 by 2 because I have 4 that I'm going to look at. And I'll go ahead and create a plot of just the diagonal. These are scaled values, so I'm just going to go 2 to 2. Mean is 0, standard deviation of 1. So I'm just going to create what I would say is the perfect solution, and I'll just have that be a black line. All right, and then what I want to do now is go ahead and put on my predicted and measured values. Okay, so I have my method predict, and I'll have X train, and then I'll put on Y train. So there are my measured values, and I'll do R0, and label is going to be training, and then also, because I have that name there, I'll just say name plus train. Okay, and then the second one, it's going to be very similar, but now instead of that Y train, I'm going to just replace these with the test. Okay, so test and test. Okay, let me change the color of those to blue X's, and I'll just change this to test as well. Okay, and I'll say for I in 3, 4. Okay, so just for the last 2, I'll put on an X label. And then for I in 1 and 3, these are where I want it on the Y-axis, the label there. I'll put Y label, and that's going to be measured. Okay, so that one did not work out well. Let me see what's going on here. Let's see, Axe is currently an early instance. In a future version, a new instance will always be created and returned. Okay, so it didn't like something about what I'm doing here. Let me just see if I can figure this out. Okay, I'm incrementing it. I say that, okay, X label, Y label, put on the legend. Okay, I don't see the, it looks like it's putting it all on the same one. Okay, for some reason it's not splitting it up into those individual ones. So let's go ahead and just, I don't know, maybe go ahead and just create separate plots. I'll do that for now until I can figure it out. Okay, I won't create a separate subplot. I'll just create these with predicted and measured. Okay, so there's linear regression. It's going to start scrolling now. Maybe I should make this just a little less large as well. Okay, I'll let it scale it down to a better size. Okay, so there's linear regression for the train and the test. And so you can see if it was perfect, they would all line up right along here. So this is what I'm predicting, and this is what I'm measuring. And you can see this parity plot, this scatter plot that shows if it's off of that black line, then it's not a perfect prediction. All right, and here you can see support vector regressor. You can see a much tighter cluster here. This would perform much better than linear regression. And you could also see k-nearest neighbors. It performed really well right here for the training, but when we got to the test set, you can see a much wider scatter, similar to what you saw with the linear regression. And this is the neural network. This did a better job, along with support vector regressor, for both the testing and the train set. All right, let's go on, just do one more. I'm going to do a joint plot that shows two variables with the univariate and joint distributions. So I'll do a joint plot with seaborne, and I'll say that y equals cement and x equals CSMPA. And data equals dpair. And kind, I'll say KDE. You can also use other types. And then hue is going to be equal to strength. Okay, so this is our high and low plots, just a parity plot between the two. This shows cement. Okay, the cement concentration in kilograms per meter cubed versus the concrete strength. And so you can see the distributions of those with this. Okay, that was a rather long exercise. I'm just going to go back and summarize what we've covered so far. So we did some visualization as a first step. Again, there's that video right here, but then we got into classification and regression in this second one, where we went through a number of these different classification methods. And if you want to dig into it just a little bit more for each of these, you can see some of the theory in the background for each of them, how they work, and some very simple case studies here that show how each of those classifiers or regressors work. Okay, so we covered 8 of those on classification to classify between high and low strength for the concrete. And then 4 of these for regression. We didn't do XGBoost regressor, but that's also a very good one. XGBoost classifier is also a very good one for both of those. Okay, so I hope you enjoyed this. Again, just I'll post this video here as well, and hopefully you've enjoyed this case study.